Hi, my name is Manish Gupta, and in this video, I'm going to talk about NGAME, which is negative mining aware mini batching for XC for extreme classification. So let's get started. Let's get started with what is NGAME's architecture. So as I just mentioned, NGAME stands for negative mining aware mini batching. It's a transformer based method for extreme classification. In fact, it basically uses the Siamese architecture. So it's a transformer based Siamese architecture for extreme classification tasks. Uh, it basically is special because if you think about the deep XML pipeline, it actually involves majorly two modules, M1 and M4 in that senses. Okay, so basically because it has a special in-batch sampling based negative mining technique, and this technique is actually used in both M1 as well as in M4. So you could think of it as a special module, or you could basically fold it in M1 and M4. Okay. So in the usual notations, let's just basically recall them. So if L is the number of labels, and remember in extreme classification tasks, the number of labels could be very large, right? V is the vocabulary size. So this basically includes the vocabulary for data points as well as for labels. N is the number of training points. So where each training point basically is essentially something like this document. And yi basically says whether the label, for example, this label is relevant or not, right? So -1 or +1. Uh, so NGAME basically uses a 6-layer Distilbert encoder for embedding these data points as well as labels. So as you see, the first step is to basically use a 6-layer Distilbert based encoder, take the CLS token, and that's basically the embedding for both the data points as well as the labels. Okay. And then, so of course, these parameters theta need to be trained. So that's basically that, but you initialize using Distilbert base. Okay. NGAME also learns these Ws, which are essentially the free parameters standing for the classifiers, right? So essentially they are one versus all classifiers, and essentially these one versus all classifiers, we will see how they are exactly computed. But Ws are the notations we'll use for the one versus all classifiers. And of course, there's a classifier per label. Okay, so that's that. Now, inference pipeline actually is pretty simple. So, so once you have basically trained these Ws and you have your embedding parameters also trained theta, the idea is that after your training is done, you essentially index all the classifiers W into an approximate nearest neighbor search index. Okay, so essentially it could be HNSW or any other such approximate nearest neighbor search index. You index all of these Ws into that index. Now, when a training point comes in, you essentially pass the training point through this embedding block and essentially get its embedding. This embedding is used to query the approximate nearest neighbor search index so as to get the labels with high classifier scores. So the classifier scores, of course, are going to be computed as sort of a cosine similarity between the classifier WL and the embedding representation for the test point XT. But you essentially, that's what you do. You just find nearest neighbors using the approximate nearest neighbor search index lookup. And more or less, that's basically the ranking scores that you could directly use so as to do inference. Of course, you can combine these scores, as we'll discuss later, with the other kinds of scores as to get a better ranking. But mostly this kind of ranking also works reasonably good. Okay. So now let's talk about how is NGAME trained. So we have already understood that NGAME is basically a transformer-based Siamese network architecture. Now, how is it trained, right? So basically, the training follows the deep XML pipeline. Recall, if you've not looked at that video, please look at the deep XML video. It basically contains 4 phases, M1, M2, M3, M4, where M1 basically stands for encoder training, M2 essentially is for negative mining, M3 is for reinitialization of various parameters, and M4 is basically the fine-tuning stage. Okay. So let's basically think about how does the deep XML pipeline apply for NGAME. Okay. So NGAME, of course, so basically it's a modular training using deep XML pipeline. M1 basically is for encoder training. So you can think about it as a pre-training stage in some ways. So of course, you start with Distilbert base, and that's how you initialize your theta parameters for the embedding block. But the idea is that and here you don't really bother about the Ws at all. You essentially have your data points, you have positive data points, negative data points, and so on for every. So for every data point, you have positive labels and negative labels, right? You don't use all the negative labels because using all the negative labels would take a lot of inference time or training time, right? So therefore, you sample using negative mining technique that I'm going to talk about on the next slide in more detail. But you sample a few negative labels and a few positive labels for a particular data point, for every data point, right? And what you want to do is to ensure that the similarity between the data point and positive labels is higher compared to the similarity between the data point and the negative labels by at least a margin gamma. Okay, so that's basically the kind of training you want to do. Okay. So during this training, what you're trying to learn is basically these thetas. So you're basically trying to learn these thetas, the embedding block, basically. Right? That's that. Now, M2 essentially is negative mining typically in deep XML pipeline, but there is no special M2 in NGAME. It's basically subsumed in M1 and M4. So essentially, how do you get these negative labels is basically using the negative mining technique that I'll talk about on the next slide. Okay. Now, in M3, essentially you freeze your thetas. Your embedding block is basically trained. You freeze them, okay, and you initialize your weight vectors your classifiers with just the embedding representation for a label data point. So you actually use label text. So essentially you use label text and you essentially get the representation ZL, and that is what you basically set your initialize your WL with. So, or other, embedding E theta of ZL. So ZL is, this is E theta of ZL. So essentially you have already processed your ZL label text with the embedding block, and that is how you initialize your classifiers. Now in M4, you're basically going to learn, of course, your classifiers. So the way you learn them is basically using what you have initialized with E theta of ZL plus these free vectors eta L. And these free vectors are there so as to learn associations between data point and the labels from the trained data, right? So while doing this, you're basically trying to you essentially fixed E theta. So theta is fixed. So theta you don't really bother about. So that's no longer a variable. You're essentially going to only update your Ws, learn your Ws, of course, by learning these eta Ls on the way. Okay. So and the loss is pretty obvious that you want to ensure that a data point and the classifier, the classifier score for the label for the positive label should be greater than classifier score for the data point for the negative label, at least by a margin gamma. And you do this for a few selected positive labels and a few selected negative labels for every training point, each of those n training points. Okay. Now, again, since you're using some negative labels, it's basically taking help from the negative mining technique, which I'll basically discuss on the next slide. Okay. So as you see, M1 basically does the encoder training. M4 essentially does the classifier training, right? So M1 is basically encoder. M4 is basically classifier training. Splitting this encoder and classifier training essentially also helps with memory overheads in each module, right? So ease out memory overhead. So this basically means that you could actually afford to train with larger batch sizes, which makes training faster and more accurate as well. Okay. Now, the other interesting part is that your embeddings are actually fixed in M4. So in M4, your embeddings are fixed, which basically means that to be able to learn these Ws, you can actually learn them in a distributed manner across multiple GPUs. So by splitting the label set into different partitions and learn classifiers independently for each split of those label set. Okay, so that's another benefit or advantage that you can do distributed training without GPU communication at all. Okay. So now the only puzzle, the only thing in the puzzle is basically how is negative mining done, right? So how is negative mining done? NGAME actually believes in a very interesting negative mining strategy. Okay, so the first thing that it does is to essentially do clustering by using cluster all the data points using embeddings E theta of xi. So essentially you have your data points, right? You have your data points xi. You essentially pass them, of course, in the beginning, your embedding block is essentially just a Distilbert base. So you pass them to Distilbert base, get an embedding for every data point, and then you cluster them. Okay. So after your embeddings are obtained, you cluster them. And you cluster them using hierarchical k-means. So that's how you cluster them. So you have a cluster, you have clusters of data points, and how many clusters? Well, n by c clusters. So c is essentially a hyperparameter here. What should be the cluster size? So that basically gives you n by c clusters. Okay. So of course, you're going to do that t times. So essentially several times. Okay, multiple times you're going to do this. What are you going to do? What are you going to do? Well, you're going to use the current embedding block, and you're going to cluster your data points. And after you have obtained the clusters, you are going to pick up a few clusters. So randomly choose S by C clusters. So how many? What is S? S is the mini batch size. So you're going to update your thetas, right? So you're going to update your thetas, and you're going to do that using batchwise gradient descent. So so in a particular batch, you're going to include clusters of data points, okay, to create a mini batch ST at time point t of size S. Okay. Now, You take all the positive labels for each data point I in S, and you basically say that's your positive label set, okay, that you'll care for. Negative labels, the way you do the negative labels is to essentially first compute the embeddings for the data points. You compute the embeddings for all the labels that are present in your all the positive label set. So remember, ZL is so ZL is essentially in LT. So in the sense that whatever the positive labels for this particular batch, you basically take its embeddings, and we are going to basically get hard negatives by looking for those labels to be associated with I as hard negatives, such that um, the embeddings for the data point and that particular label ZL is are very close to each other. Okay, so the idea is as follows. You first have clustered data points. Now, clustering data points means that you have put up all those data points which are close to each other. Okay, so you have put up all those data points which are close to each other in the same cluster. Now, you basically say that if I have a particular data point, blue star, right? This is my data point. I have other data points here. I have other data points here. Okay, they are associated with these red guys. Okay, they are associated with these red guys, which are the labels. So red ones are the labels. Red ones are the labels. Okay, red is label. Okay, red is label, and if you think about it, these stars are basically data points. So these are data points. So you find another data point which is close by and look at its labels. So now, of course, this particular data point is associated with these positive labels, which are denoted by the green plus. So green plus are the positive labels. It is linked to them anyway. But within the cluster, you're going to look at other data points, these light stars, right? And then look at their labels. So this is a very good negative. This is a hard negative. These are hard negatives. Okay, these are all hard negatives. Okay. Now, of course, these ones, these unfilled red circles are also hard negatives, but it misses them. NGAME misses them because they're in a different cluster. Remember, you're going to basically sample hard negatives only from the same cluster. Okay, so hard negatives are those labels which are positive for other data points in the same cluster. Okay, it is as simple as that. Hard negatives are those irrelevant labels whose embeddings are very similar to the data point. Okay, why are they similar to the data point? Because, well, you have clustered the data point themselves anyway, and you are basically looking at positive labels of those data points. So if clustering was done well, embedding was done well, then those other points in the cluster are very similar to the current data point, and their labels are also similar. And if they are negative, then they're hard negatives, right? So if they're negative, if they're irrelevant for this data point, then they are hard negative labels. Okay. So that's that. The only problem is that NGAME only misses only on those hard negative labels for a data point that are not in this same cluster, that are negative and they are not in the same cluster. But that's okay because cluster sizes are large, so boundaries are not that common. So therefore, it's okay. Okay. In fact, this way of sampling actually makes in-batch sampling really very efficient and effective. Okay. So typically, remember, in-batch sampling suffers from this problem of tail labels and so on. Now that problem doesn't happen here. Why? Because, well, here you're going to get really hard negative labels, which are very similar to the current data point, thanks to the clustering step that you did before. So your in-batch sampling is going to contain coherent data points and labels, or similar data points and labels, right? Also, it is inexpensive. Why is it inexpensive? Because these hard negatives are not really sampled from anywhere and everywhere else. They are actually positives for some other data points in the same batch. So therefore, you're doing sampling and embedding computation for in-batch labels only. Okay, so therefore, this is very inexpensive also. Okay. And well, I mean, after you've basically figured out positives and negative labels for a data point, you're going to update you're going to essentially update your thetas using the mini batch, using this optimization function, right? Using mini batch gradient descent, using that optimization function. Okay, so that's that. Now, the interesting part is that this clustering step, I mean, in the in-batch sampling strategy, the clustering step essentially just consumes 1% increase in time over vanilla in-batch sampling, right? So basically, the clustering step just has an overhead of 1% amount of time, epoch time. Okay. Now, notice that as you are updating your thetas more and more, essentially your clustering improves because you're trying to do clustering after every step, after every gradient descent step, right? So essentially, it continuously adapts its negatives. Its negatives become more and more, hard in that senses. to the progress or the the embeddings basically become better, right? So essentially, therefore, your negatives become better as the training progresses. Okay. In fact, they also do curriculum learning by actually also increasing. They start with a small c, so they start with a smaller cluster size to begin with, and then after every 25 epochs, they actually increase the cluster size. Okay. So remember, if the cluster size is small, the negatives are not so hard. Right. So essentially, if the cluster size is small, the negatives are not very hard. So basically, the idea is that they follow the curriculum learning strategy that you should basically learn with simple examples first and then make it more and more complex as the training progresses. Okay. So how does NGAME perform? So NGAME has this nice modular structure. It basically does in first M1 stage, it basically does encoder training. And then in the last stage, in some ways, M4 stage, it basically does the classifier training, right? So it has a modular structure and it has this nice negative mining strategy. How does it perform? So now to perform, again, I mean, for inference, you could directly use the classifier scores as we discussed here, right? So essentially, you could directly make use of these classifier scores, and that's basically your overall output score. So you can rank by that score, rank labels by that score, or you could actually also learn a regression tree over not just classifier scores, but also these other two things, approximate nearest neighbor search similarity, right? So remember, you are going to do a lookup on the index, which basically approximate nearest neighbor search index, which basically also encodes your classifiers, right? So, and also you could use frequency of label in the dataset as an extra feature. You can learn a regression tree on top of this. And then after you have trained this tree, you could basically make use of this tree. In some ways, it's more like a combiner. It basically takes your encoder scores from approximate nearest neighbor search index and your classifier scores and the frequency of label in the dataset and nicely gives you a score based on all of these three as features. Okay. Overall, NGAME has these four hyperparameters: cluster size, right? Batch size, interval between clustering updates. So you don't really update the clusters at every time step because that will be too expensive. So maybe you can update the clusters after once every 5 steps or 10 steps and so on. Okay. So and then margin gamma. So essentially, what is the margin while you are actually solving the Siamese loss, while you're trying to do the Siamese loss, right? So that's that. Of course, NGAME was shown to be better than several other XC methods, extreme classification methods, on multiple benchmark full text and short text data sets. So compared to Siamese XML, Eclair, and decaf, it could perform 16% better in terms of P at 1. And in terms of P at K and precision at K and PSP at K, it could basically be 13 and 15% better than other methods like light XML and XR transformer. Even on short data sets, you see similar kind of trends. Now, what is interesting is that if you really plot contribution of NGAME, to precision at 5, this metric, you basically observe, and this is plotted across deciles. So this is decreasing frequency, which basically means that these deciles are head deciles. They have very high frequency deciles of labels, while these basically have low frequency. So these are tail deciles. So what you observe is that the contribution by the tail labels to the precision at 5 is significantly large, which basically means that NGAME not just performs better compared to other baseline methods overall, but also performs nicely, does good predictions for rare labels accurately. Okay. Now on Bing, basically folks actually used NGAME to do two interesting tasks. So predicting queries for web pages to show ads. Now on that task, it was observed that NGAME actually increased CTR and click yield by significant amounts, very large amounts. Okay, CTR is click-through rate. So essentially, what is the probability that somebody would click on an ad if you show that ad? And click yield basically is the rate at which an ad is clicked with respect to total number of searches. Okay. So essentially, CTR in the denominator, you have total number of impressions of the ad, while in the denominator for click yield, you essentially have total number of searches rather than total number of impressions of the ad. Okay. So that's that. Now, so basically, these are massive improvements, right? So in fact, if you think about other problems, so click the web page to predict queries. So essentially, you have a web page title and you want to figure out which queries this web page could be clicked for, right? So the label space is pretty large here. I mean, all possible queries, millions of queries there, right? And the NGAME was shown to be 2% better at recall at 5 than Siamese XML. Okay. So in summary, NGAME basically involves negative mining aware mini batch creation. So you see mini batch creation, the way it was done is essentially to cluster data points such that labels, positive labels of other data points in the same batch are hard negatives for this particular data point, right? So it's negative mining aware mini batch creation. And NGAME trains in a modular way. Siamese, it trains Siamese extreme classification method with one module training the encoder, the other module training the classifier. Okay. It has been shown to be significantly better than previously proposed extreme classification methods, more accurate predictions compared to light XML XR transformers, also huge gains in click-through rate over an ensemble of very good generative extreme classification, information retrieval, and Siamese models for ads, right? So as of today, in fact, NGAME is the best extreme classification method out there. So you might want to try it out. Okay. Okay, hope you like the video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.